So they say 5.7 day 2. This is actually just going to be day 1, and then we'll have a part 2 that we'll do tomorrow. So we're going to talk about optimization. It still involves finding the derivative, but it's also going to involve our favorite word problems. Yay! So in example 1, we want to find two positive numbers whose sum is 60 with a maximum product. So we've got two things going on here. First thing we want to do is look at the first sentence. We want to find two positive numbers whose sum is 60. Bless you. So I'm going to call my positive numbers just x and y. Sum means that I'm going to add them together, so we can say x plus y equals 60. Now this doesn't change. This equation we're going to call our constraint. The second part of this question says that they have a maximum product. So in these word problems, it's going to kind of be worded like this, where it'll give you a sentence where it's going to be your constraint. It doesn't change. The second part of the question, or the second part of the word problem, is either going to ask for a maximum or minimum of something else. So the maximum product, our product of these two numbers, is going to be x times y. And I'll call it P, because it's the product. We just to give it a name. Now, since we're looking for maximum here, this is what we're going to be taking the derivative of. But before we take the derivative, we just want one variable in this equation. So I'm going to go back to my constraint and solve for one of my variables. It doesn't matter. You can solve for x or you can solve for y. I just want one of them all by itself. So I'm just going to move the y to the other side, subtract y. We get x equals 60 minus y. So I'm going to take this 60 minus y and substitute it into the x. So now I'm going to say my product equals 60 minus y times y. You can throw it away. Now we could take the derivative of it here, but we'd be doing the product rule. Let's simplify it before we take the derivative. So I can distribute the y. So our product is 60y minus y squared. Now from here, we want to take the derivative. So I'll just call it P prime. Our derivative equals 60 minus 2y. Since we're looking for a maximum, we're kind of looking for our critical numbers here, because our critical numbers would happen at a maximum or minimum. So we want to set this equal to 0. Because we're looking for a maximum. So when we set it equal to 0, I can add 2y to the other side. We get 60 equals 2y. Divide by 2. Y equals 30. So going back to the question, it says find two positive numbers whose sum is 60 with a maximum product. So we found one number. One of them is 30. How do you think we could find the other number? Remember we said x and y. We found y. How do we find x? Plug it in. So we can take y, plug it into our constraint here. So x plus 30 equals 60. What does x equal? 30. So 30 and 30 are two numbers that give us a maximum product. So kind of looking back at this question, we're looking for two positive numbers whose sum is 60. So 30 plus 30 would be 60. With a maximum product, what's 30 times 30? 900. If I were to pick two other numbers whose sum is 60, let's say I had 29 times 31. 29 plus 31, the sum is 60, but what's 29 times 31? Not as big as 900. It's actually 899. So we're going to find two positive numbers whose product is 400 and whose sum is a maximum. So starting with our first sentence here, find two positive numbers whose product is 400. How could I write that in an equation? X times y equals 400. Awesome. Product means multiply. This is going to be our constraint. We don't take the derivative of this one. This is our constraint. Doesn't change. Next part of this word problem says whose sum is a maximum. How would I write this in an equation? It would be x. We're just looking for whose sum is a maximum. So we can call it sum. We'll name it as a sum is equal to x plus y. We'll find the derivative to handle the maximum part. But before we take the derivative, we need all of our variables to be the same in our equation. So I can solve my constraint for either x or y. It doesn't matter. I'll move y to the other side. So we have x equals 400 over y. And then I can take this and substitute it into the x here. So our sum equals 400 over y plus y. Now we want to take the derivative. Before I take the derivative, just to make our lives a little bit easier, how else could I write 400 over y? Awesome. 400 times y to the power of negative 1. Perfect. Just will make it easier. That way we won't have to do the quotient rule. Now we can take the derivative. I'll call it s prime is equal to negative 400 y to the power of negative 2. What's the derivative of y? 1. So then our derivative would be negative 400 over y squared plus 1. What would I do next? How would I find where my sum is a maximum? What do we do in the last one? Awesome. Set it equal to 0 and we're going to solve for y. So I can add the 400 over y squared to the other side. So I get 1 equals 400 over y squared. We can multiply both sides by y squared. So y squared equals 400. Take the square root. What would y equal? So y would equal 20. Why is it not plus or minus 20? What does the question say? Find two positive numbers. So we just care about positive 20. So y equals 20. How would I find x now? Plug it into the constraint. So I have x times 20 equals 400, or I can plug it into my simplified constraint here. So x equals 400 over 20. So x equals 20. It's not always going to be the case that both of these numbers are equal. It just so happens for the first two examples. A manufacturer wants to design a can that holds 1,000 centimeters cubed of liquid while minimizing the amount of material needed for each can. So let's separate this into our two equations here. A manufacturer wants to design a can that holds 1,000 centimeters of liquid. So if we're talking about how much liquid is in a can, what do you think type of equation we need here? The volume. Awesome. our volume equation of a can, so this would be like volume of a cylinder, would be pi r squared h. And our volume equals 1,000. So this is our constraint. Let's move on to our second part of the equation. It says, while minimizing the amount of material needed for each can. What do you think type of equation I have when I'm talking about the material that's covering the can? Surface area. Awesome. Our surface area equation for a cylinder is 2 pi r times h plus 2 pi r squared. So looking at my surface area equation, it'd probably be easiest to find what h is equal to, and then I can substitute that into my h, just because I only have one h in this equation. You could solve for r and then substitute it into r, but you'd be doing more work. So it doesn't matter. Just like in the last example, we solved for x and then plugged that into the x and solved for y in our second equation. You could have done it the opposite way. So it doesn't matter. But here, looking at our surface area equation, since there's only one h, I feel like it'll be easier. Let's take our constraint and solve for h. So in our constraint, when we solve for h, I just have to divide pi r squared to the other side. So we'd get 1,000 over pi r squared. Now we're going to take this and substitute it into the h in our surface area. So our surface area is equal to 2 pi r times our new h, which is 1,000, over pi r squared. Plus 2 pi r squared. Let's simplify this before we have to take the derivative. So when I'm multiplying here, I could cancel out the pi's because I have a pi on top and a pi on the bottom. And then I also have an r on top, and I can take out one r on the bottom. So here I'm left with 2,000 on top over r plus 2 pi r squared. Now I need to take the derivative of this. Before I take the derivative, what's a better way that I could write it that'll make finding the derivative easier? Awesome. Let's move the r to the top. So 2,000 times r to the power of -1. Now when we take the derivative, we get negative 2,000 r to the power of -2. Then when we take the derivative of 2 pi r squared, what would our derivative be here? 4 pi r, perfect. Because that 2 pi is just a coefficient. It's just the number out front. So here would be our derivative. What would we do next? Set it equal to 0. I'm going to rewrite it just to make it a little bit easier for us to solve. So we have negative 2,000 over r squared plus 4 pi r. Now we set it equal to 0. To find our minimum here. So I can add 2,000 over r squared to move it to the other side. So 4 pi r is equal to 2,000 over r squared. What can we do next to solve? Multiply both sides by r squared. So it cancels out on the right. We get 4 pi r cubed equals 2,000. Then what? Awesome. Divide by 4 pi. This one, since we have a pi in here, we need our calculator. I think I wrote it down. 2,000 divided by 4 pi would be 159.15. It keeps going, but just leave it in your calculator. What would be the last step that we have to do? Cube root both sides. Get rid of that third power by cube rooting both sides. So r is equal to the cubed root of 159.15, which should give us 5.419. Now here we're not just talking about a number like we were in example 1 and 2. We're talking about material. It gives us a unit here. What unit would our R be? Centimeters, awesome, because it gave us the volume of centimeters cubed, so our radius would be just centimeters. Now what else do we have to find? We have to find the height. So what could I do to find the height? Awesome. We're going to plug in r into our first equation, or I can plug it into the simplified first equation here. So h is equal to 1,000 over pi times 5.419 squared. When we put this into the calculator, we get 10.8 centimeters. So example 3 says a dairy farmer plans to fence in a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimension would require the least amount of fencing if no fence is needed along the river? So we're going to look at the first part first. So dairy farmer plants fence in a rectangular pasture adjacent to the river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. Sometimes when you have word problems like this, it might be helpful to draw the picture. I've got a square fence along a river. Your pictures don't have to be as pretty as mine are, but sometimes it helps to see it. So the pasture must contain 180,000 square meters in order to provide enough grass for the herd. So we're talking about how much grass is inside of our fence here. What do you think type of equation I would have? Area, awesome. So our first equation is going to be the area of a rectangle, which we can call length times width. And what is our area? $180,000. It's a big number. All right, so there's our first equation. This is our constraint. This one does not change. Next, let's look at our second equation. What dimensions would require the least amount of fencing if no fence is needed along the river? So we're talking about the amount of fencing we have if no fence is needed along the river. So we've got fencing on 3 sides of our rectangle. So we're dealing with the perimeter formula, but it's just the perimeter of 3 sides. So we can call it length plus width plus length, or it would be 2L plus W, because we've got 2 lengths there. It really doesn't matter. You can call it base times height if you wanted to. They're just variables. So if you had 2 widths and a length, it wouldn't matter. So which variable should I solve for here? We could find what L equals and then plug that in. I think it would be easier to find what W equals, just because in our perimeter equation here, we only have 1 W, nothing's happening to it. If I plugged in something for L, I would have to multiply it by 2. It doesn't matter. You can solve for either one. So let's find W. How would I solve for W in my constraint? W equals 180,000 over L. Perfect. So let's plug that into our W here. So we have our perimeter equals 2L plus 180,000 over L. Let's simplify before we find our derivative. So we have 2L plus, I'll call it 180,000 times L to the power of -1. Now we can find our derivative. What's the derivative of 2L? 2 plus, or actually this would be minus now, minus 180,000 times L to the power of -2, so I'll just put it over L squared. Any questions on what I just did there? Awesome. What should we do next? Set our derivative equal to 0. Perfect. I'm going to add the 180,000 over L squared to the other side. What would we do next? Multiply both sides by L squared. So 2L squared equals 180,000. We can divide both sides by 2. So L squared equals 90,000. What's next? Take the square root of both sides. So L equals what? 300. Perfect. 300 what? Meters. Great. So that would be our length. We found one of our dimensions. How would we find the width now? Plug it in. We can plug it into our simplified constraint here, since this one's already solved for W. So W equals 180,000 over 300. So we would get W equals 600. 600 what? Meters. Perfect. So a rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular corrals. So let's draw that first. We've got 2 rectangular corrals that are next to each other. What dimension should be used? So the enclosed, this should be area. It's missing an A. The enclosed area will be a maximum. So starting with our first sentence, let's find our constraint first. A rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular corrals. So I drew my corrals here. Let's give them units. You can call it base and height if you wanted to. Here I'm going to call it X and Y. So let's say one of them, this would just be X. So I've got X plus X on one side, X and X here, and then I'll call the length or the height or whatever Y. "200 feet of fencing to enclose 2 adjacent rectangular corrals." How would I write that in an equation? What are we talking about? Perimeter. Awesome. So perimeter, we just add up all the sides. So our perimeter would be, how many X's do we have here? 4 X's. And how many Y's? 3 Y's. So this is our constraint. Let's move on to the second part. What dimension should be used so that the enclosed area will be max? What am I looking for here? The area. So our area of just one of the rectangles would be what? X times y. So the length of the rectangle times y. And then we have another rectangle that's the same length and width. So it would be 2x times y. Or you call it x times y plus x times y. So now here we could either solve for x or we could solve for y. It doesn't matter. What does our perimeter equal? I forgot one thing in our constraint here. 200, perfect. Let's solve for x. So I'm going to subtract 3y to the other side. So 4x equals 200 minus 3y. Divide by 4. X equals, what's 200 divided by 4? 50 minus, we'll call it 3/4 y. Now we can take this and substitute it into the x here. So when we take our derivative, we only want one variable in that equation. So we have 2 times 50 minus 3/4 y times y. We could totally find the product rule here when we do our derivative, but let's simplify it to make it a little bit easier for us. I can distribute the 2 to everything, and I can distribute the y to everything. I'll do the 2 first, just so we could do it at once. It doesn't really matter. So 2 times 50 would be 100 times y, so 100y. And then 2 times negative 3/4 would be 6/4, which simplifies to 3/2, so minus 3/2 times y would be y squared. What do we do next? Take the derivative. So our derivative of our area would be 100 minus 3y. What do we do next? Set it equal to 0. So I have 100 equals 3y. Divide by 3. So y is 100/3. 100/3 what? Feet, perfect. Now how would we find x? We can plug it into our simplified equation here. So x equals 50 minus 3/4 times 100/3. Here the 3's cancel, and 4 goes into 100 how many times? 25. So we get x equals 50 minus 25. So x equals 25. 25 what? Feet, perfect. So our dimensions would be 25 and 100/3.